Right, welcome everybody. So today we're going to begin the final unit of the semester, and we'll introduce a concept which I think you'll actually find pretty straightforward and very logical called object-oriented programming. This new concept we'll be looking at gives us the ability to model objects, such as pizza, which we'll be looking at today. And you can imagine modeling objects as something in a program like ordering an online pizza, selecting your toppings, selecting the size, and so on. The slides should be updating in just a couple minutes. I just pushed them up, and we're going to jump right in to a couple of quick announcements while we're waiting on that. The first is if you are planning to continue on in computer science and you want to keep making progress over the summer, there are 2 sections of COMP110, which is the next course following this course, available. Both summer sessions. The first one's taught by Kaki Ryan, and the second one's taught by Jesse Wei. Both are great instructors who are currently graduate students in our program. Kaki Ryan is someone I've worked with for a number of years. Highly recommend taking a course with her, hoping in the future she might join our faculty as a full professor. And Jesse Wei is also great in second term. The second announcement is also targeted towards folks who are thinking about continuing on. Whether or not you're thinking about majoring or not, if you're just interested, we've got a really exciting COMP190 course. This is a 1-hour course taught by 2 students who I've been working with for the past couple years. And they're fantastic. They're undergraduates, actually. And they're designing a course that is meant to teach sort of the tools and technologies that you wish you knew and wish you were taught more explicitly in your classes. But they don't really fit into the academic curriculum very well. So more about Git, which is a tool that you've been using this semester, some editors and things. It's a very exciting course. Meets once weekly on Wednesdays. Again, it's 1 credit hour. You'll see me listed as the instructor. And if you're interested, you can look on Connect Carolina in the class info and submit a form. And I think we'll probably be doing some kind of lottery, but because the demand seems to be in excess of the seats available. However, all of the content that we produce for this course will make publicly available. So if you sign up, in the worst case, you'll get access to the public content next semester. All right, let's jump right into it. The first warm-up is actually not involving code at all. I want you to think about pizza. And there are a few questions to respond to on Gradescope. You can do this as a group of up to 3. I would encourage talking about this with a neighbor, but let's jump right into it, and I'll turn it over to you for 4 or 5 minutes to think about these questions. And we're doing this at a high, sort of rational, logical level. 1, 2, 3, go. 2 more minutes on this. 2 more minutes. One more minute. All right, let's talk through this. There are many, in fact, there are probably infinite number of ways to correctly respond to this, but does someone want to volunteer what attributes they imagine for their pizza order? This isn't a trick question. I'm sure you've got it. All right, I'm throwing you the cube. Let me make sure I don't throw my pen as well.
Like various types of toppings and like the type of crust.
All right, let me write some of these down real quick. So you said sets of toppings. Oh my gosh. Let me try this again. Crust. What else did you have?
I don't know, like, I guess if you want like an extra type of something, like extra cheese or something.
Extra cheese. Anything else?
Like how big?
Size, yeah. All right. So we can take some of these and we can start imagining Python types. For example, what type might you use extra cheese for extra cheese?
A bool value?
Boolean. Yeah. What about size?
Probably either a stir or an int, I'm not sure.
Yeah, so that's a great observation. Could be stir, could be int. So what would a stir be? What would an example of a string be?
Like large?
Large, small, and you can define these sizes. And then an int, what would that represent?
Like the inches?
The inches of diameter, yeah. And so when we start to talk about today's subject, object-oriented programming, these types of decisions, how do we model some object? Do we use a string for size? Do we use an int for size? This is part of what we call the design process. And it's up to you as the programmer and the problem that you're trying to solve and maybe the business that you're serving or the organization that you're working for to figure out what is the right type of attribute to decide upon for a given object or what we'll see is called a class very soon. For sets of toppings, how would you imagine that as a Python data type?
I feel like maybe stir or like an int of like the amount of toppings you want.
So an int number is one way of looking at this. You could imagine doing a set of strings, but I really like these. So toppings, maybe as an integer, extra cheese as a Boolean, size as a string. And we may even simplify this down a little bit further to have, maybe we won't have extra cheese in our model, but you can imagine making these decisions. You could go even deeper. What's the crust? What type of sauce do you want? There's many different ways you can imagine modeling a given pizza. Great job there. I'll have you throw the die. You got it. Anyone want to give given these three choices, and let's say size for our purposes is either large or small. Anyone want to give a favorite pizza order based on these three attributes real quickly? I'll give one. I ordered this the other day. I had a medium, well, shoot, I said large or small. We're going to call it a small pizza from Domino's that had 2 toppings, and our model is not going to actually specify which they were, but for your enjoyment, they were ham and pineapple. Another common one is, yeah, it is a Hawaiian. Another common, ham and pepperoni is also surprisingly good. There is not extra cheese, right? So this was Chris's order. Anyone else have a favorite pizza order they'd propose if you were ordering pizza for you tonight? Anyone have a ridiculous one? No one wants to, oh, here we go. Coming at you. Watch your heads.
I'm a big fan of barbecue chicken pizza.
Barbecue chicken pizza. How many toppings would that have on it?
Just chicken, pineapple, and onion if I have a coupon or something like that.
All right, so 3 toppings. If we had modeled sauce, we'd get barbecue sauce in there. I'm going to imagine you ordered a large because you wanted some leftovers. And what's your name? How would you spell that for me? Great. So Namit has a large 3-topping pizza. Would you throw extra cheese on that or no? Sure. Sure, yeah, so we got extra cheese here. All right, the point that I want to drive home that hopefully feels like so obvious that you might wonder why we're even talking about it is we can specify a pizza in our hypothetical world or business is modeled with 3 different attributes: toppings, extra cheese, and size. But that just says, here's this, like the domain of possible pizza. Here's what a pizza is and what it can have as its model. But if we want to think about specific pizzas that we might order or actually go cook or send back to the kitchen, we have to have individual instances where we have specific values for these things, such as the exact size that we want the pizza to be, the number of toppings. And we can have many instances of this. In fact, in a given night, a pizza shop is probably producing tens to hundreds of pizzas, each with their own variations. Some might be duplicates of one another, but they would still be individual objects, even if they had the same attributes. You can have 2 pizzas with the same attributes, and that's fine. And if we wanted to imagine a pricing model, just because this will set an example, we can imagine maybe the base price of large is, I don't know, $12, and small is, say, $8. Topping, maybe it's like $1 per. And extra cheese is, say, $2.50. And so from this, we can imagine, given these attributes, we can go and compute a price, and we'll look at how we might do that very soon. All right, so given this sort of context, I want to introduce to you the notion of a class and tell you that it gives us the ability to model new data types. And so pizza is the brand new data type that we're modeling. Python does not have any notion of a pizza built into it. We're going to introduce this type by introducing a new class definition. So I want to start first by working through this with some notes in hand, and then we'll jump into actual code and work this up together. So if we want to define a class, we use the class keyword. Right? So this is a keyword that defines a new class. When we define a new class, we're defining a new data type. And this is pretty exciting. That means we get to invent our own types in our programs. and we can model problems in a way that feels a little bit closer to the domain that we're working in. So here we're working in the notion of a pizza shop. We're modeling the concept of a pizza, so let's name this class pizza. Right? And so just like with a function definition, your identifier is followed by a colon. Right? And this will start off our class definition. But I want to make a quick note about a class name. Class names are identifiers that are camel case or proper camel cased. What does this mean? So you'll notice that we begin this with a capital P as opposed to our function definitions, which we tended to write as lowercase first starting letters. That's one piece. That's the proper piece of this. And then for introducing the idea of camel casing, it's this notion that when we have two words we want to join together into a single identifier, we don't put an underscore between them. We make the subsequent letters capitalized. And so this gives us this notion that camel and case could be two words. We bring them together. We make that second C capitalized. And why is it given this name? Well, you can imagine a long class name. If you visualize the outline of this, at each of the capital letters, you get a hump, and that's where the name camel case comes from. The programmer that decided this was quite silly, but just to give you a sense of where it comes from. The other type of naming that you've seen in this course is snake case. That's where the words are separated by underscores. Let me make that clear. And snake case variable or snake case identifier names get their name from Python. The programming language that we're using was the first that made this naming convention a little bit more popular, and the snake is a reference to Python, the programming language. So why these two different variations? Well, with class names, when you see that capital P, you're getting the sense that we have a user-defined type. This is, and by that I mean you're the user, you're the programmer, and we're defining a new type. So this isn't like a built-in type like list or dict or set where we have that underscore type. Python tends to use lowercase names for its built-in proper language types. But when we define our own classes, just by convention, we use a capital letter here. You don't have to, but it's kind of weird not to, and it's confusing to other people reading your code. And this is a convention that's true across many programming languages. Okay, so we're saying we're defining a new class. Its name is pizza. And we said we had three attributes that we wanted to use to model this, the size of the pizza. So we're going to declare our attributes. So I might use orange here. So size is type str. You'll notice that I've indented this. So following that colon, on the next line, we're indenting the body of our class. Right? So our class body, we'll learn, is made up of two things. The first are the attributes. The second we'll get to. Right? So let me make a note here. This is an attribute declaration. What does this remind you of? I heard it whispered. It looks exactly like a variable declaration or a parameter declaration. But let's say it's a variable declaration. And so there's another name for attribute that we'll learn. It's called an instance variable. I'll make a note about that and explain that when we get there. It'll make a little bit more sense once we actually have instances. So let's go ahead and complete this example. So we've got size. We've got toppings. That's what we said was going to be an int. And we've got extra cheese. That we said was a bool. So right off the bat, hopefully one of the things that you can intuit about a class is we're defining a new type, and we're saying a pizza is made up of these attributes. Right? We haven't actually made any pizzas in memory yet. We don't have a pizza that we can work with, an object in our program that we can use later on, but we're saying this is what a pizza is made up of. It has a size, it has toppings, extra cheese. And you can think of a class as bundling together some values. And we'll see how that actually works in memory in just a moment. All right. So the simplest classes you tend to think of as just being a collection of attributes, and then we'll learn how we can add behaviors or capabilities to our class in just a moment. But let's go ahead and try setting up a new pizza, like my pizza, Chris's pizza. So I could, after defining the class definition, I could set up a variable like Chris. Let me make this obviously lowercase. Chris pizza is typed pizza. And this is pretty cool. Notice we're saying that Chris's pizza is going to store a value of type pizza, and that's something we invented, right? We just came up with this pizza type earlier in our program. It didn't exist in our program or Python before. We made that. But how do we actually get a new value that we can work with? And here's where we'll see another important concept that we'll actually be spending quite a bit of time on digging into shortly. But we'll give you the high-level overview here. And I'm going to write this in blue, is assigned pizza, and it looks like a function call, right? And this is going to introduce another interesting piece of terminology. This is a constructor call. So let's pause here for a moment and mention that what can we, so if we were imagining, we're going to see this in a memory diagram very shortly. In fact, I'm about to do that to the right. And let's go ahead while we're here. This will make talking through this constructor a little bit more obvious. So I'm going to just set up some space for a quick memory diagram. And let's imagine I've got my stack and my heap, and we've got our globals frame. Just like when we encounter a function definition, and we say, OK, let's enter that function's name in our current frame and assign it an ID of those lines of code on the heap. What we're going to say is we've got a class definition, so we'll enter pizza is now a name that we know, and that's going to be ID 0 class lines 1 through 4, we'll call it in our example. All right. And so you'll notice that when we encounter a class definition, we don't do anything inside of that class yet. We process the entire block of it at once, including its body, and then we'll skip past it. We'll get to Chris's pizza in just a moment. And we set up, but we do keep track. Hey, we know that there's something named pizza in our globals frame. It's associated with this definition that we found on the first 4 lines of our program. All right? Now we reach this interesting function call, or it looks like a function call. And we know that whenever we encounter a function call, we have to use name resolution rules. We look in our current frame and we say, have we seen something with this name? And yeah, we have. We've seen pizza. That's a registered name. And then we go and we look at it, and we see that this is assigned to a class and not a function. And here's how you know that you're working with a constructor, right? So if you call a function that's associated with a class, it's a special process kicks off. And what happens is, behind the scenes, Python is going to set up a new object on the heap. So ID 1. Its type will be whatever the type is that we just called. So the type here of this class on lines 1 through 4 is pizza. And then it's going to set up its attributes associated with this. So size, toppings, and extra cheese. Now, at this point in our program, none of these values are actually initialized to anything, but we have an object, ID1, and now the variable name, Chris's Pizza, is associated with this object, ID1. And this is the process of construction, right? We'll learn there's some more nuance to this soon, and we can control some of what goes on during this construction step. But for now, the big idea is we encounter what looks like a function call. We look up, we see that that's actually bound to a class, and something special happens. We set up an instance of that class in memory, and an instance of a class has all of its attributes, space to store values for all of its attributes, but no values are assigned yet. Let me pause right here and see if there are any questions on what we're looking at so far. All right. So how do we actually assign the attributes of my pizza? Well, we're going to address it. So we're going to use an assignment statement. So we're going to say Chris's Pizza. And then we're going to use, and I'm going to make this purple, and I'll make it large, a dot. This is called the dot operator. And what the dot operator does is whatever comes before it, we look at that name in memory, and we see it's ID1. OK, we're going to jump. That dot is going to cause us to jump to that reference. And now we're going to be looking at names inside of whatever it referenced. So Chris's Pizza dot says, OK, now we can address one of these specific attributes. So dot size is assigned the string large. Chris's Pizza. And then I'll consistently use, this would not be a different color in your programming language, dot toppings. But for emphasis is 2. And finally, dot extra cheese. And you're getting the point, right? So when each of these lines evaluates, the first line would say Chris's Pizza dot size is assigned large. Again, Chris's Pizza ID1 dot, boom, we jump over to ID1, and we're talking about size, and we're going to assign the string large here. So this would be large. And then on the next line, dot toppings is going to update toppings to be 2. And then on the next line, dot extra cheese, false. And I'll write that in, right? Any questions on what we're seeing here so far? Yep. Yeah, so if we had not, so the question is, is it possible for have only 2 or 3 of them to be assigned or none of them? And so if we had just written Chris's Pizza is assigned a new pizza object by calling its constructor, and that's how I would read a constructor call. Like once you're getting comfortable with this is assigned a new pizza object. That's the point of constructor. It's going to return you a reference to it or an ID of a new pizza object. If we hadn't had those 3 lines, those attributes would have been undefined. But typically, you want to be sure that your attributes are always defined and assigned. And we'll see ways of maybe having some defaults very soon, where maybe we don't, extra cheese is just false by default. Maybe we don't want to have to assign that every single time. We'll see how to do that in just a moment. Great question. It is good practice, as with variables, to always initialize. Even if you're not planning on using it, initializing to some default value will help avoid problems later on when you go and try and use a value that hasn't been assigned anything, or a variable that hasn't been assigned anything. This actually gives us a reference now for talking about attributes and why they're called instance variables, right? So I'm going to actually make a note, attribute / instance variable. And in Python, they tend to be called attributes. In other programming languages, you'll often see them instance variables. 6 one, half a dozen the other, same concept effectively for our purposes. And the idea is we have this instance, right? This is an instance of the pizza class, an object or an instance. The pizza class is on the heap, and that's saying this is what a pizza is made up of. It's made up of a size, toppings, and extra cheese attributes. But that's not, we don't have a pizza yet. It's not until we construct a pizza that we have an instance of a pizza. And inside that instance, we have these 3 variables: size, toppings, and extra cheese. You can also think of those as attributes. So that's where the name instance variables comes from. If we had constructed another one, which we'll do in code in just a moment, we could see that we would have another pizza object on the heap. You could have hundreds, thousands of pizza objects. You could have the entire history of a pizza restaurant represented as pizza objects in memory, each with their own attributes. And that's kind of the big idea. This gives us a nice way of bundling together these instance variables or these attributes so that we can treat them as one coherent object that we can pass to other parts of our program. So what we're about to do is actually write a function, and we'll do this together. We'll get this set up in code together. But to give you a preview, because we've defined this type, we can now define a function like price. We can give it a pizza of type pizza, and it can return a float. And the big idea of object-oriented programming is how nice is it that we can pass in, we can treat one object as a coherent whole and pass it around to other parts of our program. And we'll see other ways of doing this very soon. We'll actually give pizzas capabilities. But notice, because we defined class pizza, we can now use pizza as a type and pass pizza objects around to other functions and so on. We could put pizzas in lists. We can store them as values in dictionaries. And as a fun little piece of pop, I won't call it trivia, but knowledge from the last quiz, you can't store this type of pizza in a set, though. Why is that? Or use it as a key in a dictionary. Why is that? Because you'll notice that after we constructed a pizza, we mutated it. We changed its attributes. So this is a mutable object. So you can't actually put this type of pizza in a set. If you want to learn how to do that, take the next course. But yeah, we could put pizzas in lists, and we could use them as values in dictionaries. Any questions on what we're seeing here before we jump into tracing through this or writing some of this up in code? All right. So let's jump into VS Code. All right. So let me get the lights down here. I've gone ahead and jotted down what we've been talking about. set up a file. I made a directory, class19, added a file, pizza.py. You can call yours whatever you'd like. And I'll mention that just like with functions, you can have a docstring with a class that describes what's the point of this class, what's it attempting to do. You know, with this example, it's pretty straightforward, but we can make use of this construct and say that our docstring is modeling a pizza order at a restaurant. Then we're specifying our attributes, and maybe I'll make a comment in our code about this. So using the hash, we're commenting out this line of code. I'm saying these are my attribute declarations. And again, we haven't made any pizzas yet. We're just saying, here's what the idea of a pizza is like in our program, or when we're trying to model one, and we want to go compute its price. Similarly, there's a great analogy with a social media profile. So on, say, Instagram, the idea of an Instagram profile is you have a handle, maybe you have a bio, you have a link, and then you have whether or not your profile is public or private. You can imagine some of those are strings, some of those are booleans. The number of followers you have is an int, and so on. But everyone's individual Instagram account or profile is an instance of that class. Similarly here, we have a class that models the idea of a pizza, and it's not until we go and construct pizzas that we actually have values that we can work with or data stored in memory representing a pizza. And I don't want this to sound like I assume you don't recognize this, but one of the greatest disappointments as I was learning how to program, and I was reading about object-oriented programming, and how you can model things with them, and how you can create objects like pizza objects or game characters and things like that. And I thought, wow, that's really cool that the computer is capable of building a little pizza in its memory, and that probably looks and smells delicious. But obviously at this point, and I later learned that that's not at all what's happening. What I don't want you to have any disillusion of is that when we say that we're making a new pizza object, it's literally just 3 variables bundled together. Doesn't smell like anything other than sweet, sweet code, right? And we can choose what to model based on how the problem that you're solving. There's not a right way of modeling something. It depends on your particular project. Now, when we run this and we open up our REPL, you'll notice that we actually have in globals, pizza is associated with a class, and that class has a pretty long qualified name, right? Lecture.cl19.pizza, that's the package that our class is defined in, and then pizza is the class name. And similarly, when we constructed a pizza object, and so if you wanted to, go ahead and make your own, your name underscore pizza and give it some different attributes, you could. So maybe I'll do something like Sally Pizza is a pizza. Size is small. Sally loves toppings, so 10 toppings. It's an aggressive amount of toppings. Extra cheese, also true. If you can eat this with your hands, it's impressive. And we could print, Sally toppings. Oops, Sally. Great. The point is, now we have 2 pizza objects in memory, right? We have my pizza, your pizza, and they each have their own individual attributes or variables associated with them. And that should not have said extra true, that should have said extra cheese. Typing too fast. Great. So what we're going to do next is actually write a little function, and I want to set you up for it, and then I'm going to turn it over to you. So write a function that takes a pizza object as a parameter and returns the computed price based on the logic that we set up before. So base price, large is $12 and small is $8. Each topping is $1 and extra cheese is $2.50. Right? Return a float. So I'll leave it to you all to try defining this. What I'll mention is if you, again, just like we can assign to these attributes using the dot operator, you can access those attributes or read their current values by using the same operator. So when we printed crispizza.slice, that read what is the current value stored in that object in memory, or sorry, crispizza.size, that would have evaluated to large. So the dot operator is used in this case in an expression. This expression is evaluating to a string type because size type is string. Similarly, though, that's how you can access the values that you need in order to carry out this logic. So we can also set this up like we did before. So def price is pizza, and I'll make this clear with a pizza is the parameter name, type pizza returns a float, and your job is to fill in the dots. So we'll be coming around and can help with this, but let's spend 4 or 5 minutes trying to compute the price. Once you've got it, you should be able to call that function in the REPL using my pizza object, your pizza object, and get different responses back. If you finish early, you can try adding a tax parameter as well, represented as a float, and adding tax to your price. But compare notes with your neighbor, see if you've got a similar solution. 2 more minutes on this. And if you're feeling stuck, I added a little bit of scaffolding here. And again, we're assuming that only small and large are the 2 string values that size could be. One more minute. Twenty more seconds, and then we'll walk through this together. All right. So in this function, again, the big idea here is we're able to specify a single parameter of type pizza. We can pass it an object, and that pizza object now has reference to all of its attributes. It's those bundled instance variables that we can access from having a handle to this pizza object. And so we set up a variable total. You could have done this in any number of ways. I'm just declaring total as a variable. I'm not initializing it because on the next 2 lines, we have an if-else statement where we're going to initialize it one way or the other with our base price. If the pizza size is small, total will be 8. Otherwise, if it's large, the 2 possible values we're saying exist in our in this world of our business, it's going to be 12. I'll pause here because this is actually worth mentioning. Notice we're using the dot operator here, and this is how we're accessing those variables inside the pizza object. apizza.size gives us access to that size instance variable for whatever pizza object we called this function with. So we can carry on from here. We could say total is increased by the number of toppings. And if we wanted to be pedantic, apizza.toppings, we could convert this to a float explicitly. If we had a price other than 1, right, we could have multiplied it by that price and increased it in this way. We didn't have to actually explicitly change to float. As a reminder from way back early in the semester, we also don't have to multiply by 1. If you do any arithmetic with a float and an int, the int will automatically be converted to a float, just de facto standard in most programming languages, Python included. And then if we have extra cheese, we could say if a pizza.extra cheese. This is already a Boolean type, so extra cheese is a Boolean type. It's either going to evaluate to true or false, right? Then what we'll do is total plus equal 250, right? And then we'll return total. So now that we have this price function defined, and we have 2 pizza objects that we created later in our program, we can try it out in the REPL, right? So we can say price of crisp pizza, and it's $14, right? Price of Sally pizza, $28.05. Those toppings really add up, Sally. And that's pretty cool. We didn't have to write a function that took 3 attributes in that we had to pass each of them individually. We have fewer variables to keep track of. This gives us a much more coherent organization. You can imagine that some models or some classes have many tens, potentially even hundreds of attributes associated with them for very complex simulations or program modelings. Questions on what we're seeing here? So we're seeing one half, when we look at this class definition, we're seeing one half of the big idea of classes, which they allow us to model what variables will exist when we have instances of that class. So every pizza has these 3 attributes. That's sort of the data side of a class. But there's a behavioral side of the class as well. And with classes, we can also introduce new capabilities and behaviors that every pizza object can have. And this is where the notion of we're modeling some real-world concept starts to break down. We're about to give pizza, every pizza object, the ability to calculate its own price. And that sounds nonsensical if in the English language. Like you can't ask a pizza, how much are you? And it calculates a response for you, right? But this is where we start to, as we're thinking about our programs, we know that we're not working with true representations of real-world objects, but wow, it sure would be nice if every pizza object had the ability to ask it, what is your price, rather than having to define a function separately from that class and deal with that function that way. So what we're going to do next is look at how do we add behavior to a class such that all of the objects have that new capability. And this is called a method, right? So defining a method definitions. And the good news about methods is you already are well comfortable with them. There's only one new little wrinkle of an idea that's pretty cool in how a method works. But a method is just a special kind of function so that we could define a price method. And what's different is every method that we're writing in this way has a special parameter named self. And we don't have to give self a type because it's always the same type of the class. And let's say this is a method that returns a float, right? So this looks just like a function definition. The key differences are, one, it's defined inside the class body. So notice there's indentation here. This is important, right? We haven't stopped defining what a class is. This is a part of the class definition. And the second big important idea is the self parameter. And the self parameter we'll see as a reference to whatever object you call this method on. So if we said, hey, Chris's Pizza, what's your price? Self would be a reference to Chris's Pizza. If we said, Sally Pizza, what's your price? Self would be a reference to Sally's Pizza. For the purposes of this demonstration, I think rather than typing all this out again, let's just copy and modify. So I'm going to copy the lines of my price function from down below. And then I'm going to paste them here, but there's going to be a problem. And to see this problem, I'll zoom out just a little bit. You're going to want to be sure that the indentation's correct. So when you paste, you're going to be at the wrong level of indentation. As a reminder, if you select a bunch of text and press Tab, it will indent it, all that text by 1. If you press Shift-Tab, it will unindent it by 1. And so everywhere we had previously been using a pizza, we're now going to use self instead. So we're seeing these errors highlighted that say, hey, a pizza is not defined. That's because in this method definition, we're going to make use of self. Right? And that's all a method is. It's a function defined inside of a class that has a special parameter. Now, in other programming languages, you might find that they're defined with in slightly different ways. And self might be a different word. In some languages, it's the keyword this. So you'd say this dot toppings instead of self dot toppings. But it's the same idea under the hood. And in some languages, you don't have to define that parameter. But we're in Python, and I actually really like the way it makes this all explicit and comes together. So we know that we have this special parameter named self, and self is a reference to the object that the method is called on. What does that mean? Well, now that we've defined this method, what I'm trying to convince you of is that now every pizza object has the ability to respond to a method named price. So Chris_pizza.price. And notice that in my REPL here on the right-hand side of the screen, we've seen this type of a construct before, alist.append or set.add or list.pop. Those are all methods of the classes list and set and so on. We didn't define those classes, though. Here what's special is we defined the class pizza, and we introduced this price capability. And that's just this function that we call in this special way. So when I say chrispizza.price, we see that it's 14. And if I were to call price of Chris Pizza, we see that that's also 14. So I didn't remove the function definition that existed before, that existed after all, that we wrote first. We now have two ways of doing the same thing. And I'm going to leave those just as a point of comparison and to sort of try and draw the connection from where we were and where we're going. So we've been in a functional programming mindset where functions and defining functions are kind of the big idea in how we structure our programs. And notice that makes sense. Like when we were dealing with a function, we said, what is the price of Chris's pizza? We're moving in a direction that's called object-oriented programming. And so the emphasis starts to shift towards these objects. And here, in the object-oriented way of doing this, of carrying out this computation, the object comes first. Object name dot method name, and then in parentheses are arguments. Here there are none. And that's how we address, hey, Chris's Pizza, I want to call your price method. Similarly, Sally Pizza dot price is 20.5, just the same. So the big idea of a method is we've created a capability that now every object has. Anywhere you have access to a pizza object, you can call these methods on it without having to import other functions or define other functions. So how does this self parameter come to be? Well, hopefully you're kind of figuring it out because there's a relationship between the parameter that we passed first to price versus how we address this. But notice whatever method we call, or whatever object we call this method on. So in the example of chrispizza.price, chrispizza is the object we're calling this method on. That object is what is assigned to self, right? So when we do a memory diagram, we'll see that we just take what is the object we're calling this method on. That ID will be dropped into this self parameter, and that's how we know which object we're talking about inside this function call, inside this method call. Any questions on methods here? Let's add, just for a quick example, this can also have additional parameters. So we can have a parameter like tax, which is a float. And maybe we return total times tax. And this would give us the ability to say chris_pizza.price 1.05 for a 5% tax. And we get back 14.7 with that tax applied to it, right? So it is possible to add parameters to methods just like you would with functions. You add them after the self parameter. The self parameter does have to be specified first, all right? I'm going to do something never actually done before, but I think this will be worthwhile. Ignore what I'm doing for just one moment. You should leave this function definition here. I want to just real quickly print chrispizza.price and 1.10. And can we fit this all? All right, I'm going to try pulling this up on my iPad, and we should try tracing through what an example like this looks like in a memory diagram to bring this home. So I'm going to a photo. This is a brave new world we're about to live in here. All right. All right. So the big idea on how this comes together and what we need to know in order to understand object-oriented programming in the context of the semester. This is a very silly way of achieving this. I apologize for the filth on my screen. I feel very seen right now, but that's okay. Let's jump into it. So we've got a stack, obviously. We've got a heap and globals. And what we've already talked about is when we reach a definition of a class, this entire class is going to be added to our diagram as one item. So I want to actually switch this to, there we go. So we've got the class pizza. That will be ID 0, and we add ID 0, pizza, or sorry, I'm going to call this a class, on lines 3 through 23. Right? That reflection is getting me. So we ignore the rest of that, right? We jump all the way down to line 25, and we go through what we had just been through, where we set up, okay, we call a constructor here, right? So this, how do we know it's a constructor? Again, I'm repeating myself, but we look in our globals frame, we see, yeah, we know what pizza is, we see what it's associated with. It's not a function, it's a class. So we go into the steps of construction. And construction says, set up a new space in memory for a pizza object and all of its attributes. So size, toppings, and extra cheese. I've never felt more like a boomer than seeing myself taking an iPad photo. But we haven't initialized any of these attributes, right? We'll learn how to do that on Thursday, how to make this process of construction a little bit more ergonomic for the programmer and a little bit more concise. But for now, we have to go and initialize all these attributes. So line 26, 27, 28, we've already talked through these, so I'm going to move through them pretty quickly. But again, oh wait, I didn't finish this line. I need to now say, now that we have this object, which would be ID 1, we also have Chris Pizza, ID 1, in globals, right? So we have this object, great, we have a reference to it. And now on line 26, we can say chrispizza.size. Again, dot, we look at this ID, that we follow that, and we're assigning to size the string large. And then to toppings 2, and then extra cheese false. So we previously talked through those. And then what I actually wanted to focus on is what happens when we reach a method call. All right, so this is, I'm going to write this a little bit larger for emphasis. So Chris underscore pizza dot price 110. I didn't even mean to do that. It's everywhere. 10% tax. And here's where we have to understand the semantics of a method call. So we see the dot operator. Great. Rather than this just being an attribute, notice this looks like a function call. So that's how you know you're dealing with a method call. Looks like a function call, but it's preceded by a dot. And then you look at what comes before the dot, and that's the object that we're calling this on. Right? So Chris's Pizza is just the object with ID 1, right? And we look at that object and we see its type is pizza. And if we want to know if this is a valid method call, you have to say, okay, well, let's look in the class definition for this object. And we see, yeah, there's a price method. It has a tax float parameter, and self is implied, right? So how do we, this is a valid method call. How do we set up the frame for this? So the first, when we think about frames, we have to keep track of which method are we talking about. Well, we're talking about the method in the pizza class. So we'll prefix it with pizza, and then hash, and then price. Right? So you can imagine if this is a pizza restaurant, you might also have breadsticks, and breadsticks would have their own method for determining a price. So you can have multiple classes, each have the same name method, but they're specific to the class they belong to, right? So the way you calculate a breadsticks price is different from a pizza price or a brownies price. And that's why we prefix a frame with which class's method are we talking about here. We're talking about the pizza class's price method. We set up a return address just like we would, line 29. Anyway, otherwise. And then how do we set up the self parameter? And this is a big idea, so I'm going to go back to yellow here. Self is the object that the method was called on. So because Chris's Pizza was ID 1, self is also going to be ID 1, right? So this is the big idea of a method call. The way that we get self assigned is we look before the dot, we ask what object are we referencing here, and that is what's going to become self when we go and evaluate this method call. And we also had a parameter named tax. So tax was 1.10. And I'm going to delete the rest of this. Right? So we jump in, we declare a variable named total. And then we would follow through. If self.size is small, well, self is ID 1. We look at its size, it's large, that's false. So the base price is going to be, or our total price is going to be 12.0. And then we add the number of self.toppings on the next line. So on line 18, we take the current total, add to it self.toppings. Self.toppings is 2. So this would be 14.0. We check is self.extra cheese true. Self.extra cheese is false. So we skip over adding a cost for extra cheese. And then we ultimately are returning total times tax. So this would be return value of 14 plus $1.40, so 15.40 cents, and that would be the output, 15.4, right? So this works just like a function call with an extra little twist in that when you call this method, you take that reference to the object you called it on. So Chris Pizza was assigned a reference to ID 1. We copy that reference into self, and then we just treat self the same as any other object reference within the body of that particular function call, right? And yeah, it's definitely April in North Carolina. I was outside working, and that's a lot of pollen. Any questions on this particular example? The last thing I want to show you today is how to make our lives a little bit more easy when it comes to establishing maybe some default values for these attributes. So just like we've seen the ability to have default parameters or to initialize a variable immediately upon declaration, we can also initialize our attributes in this way. So let me jump back to VS Code. And this works as you would expect. Where, let's say we wanted to make extra cheese something that's by default false. If we were to assign a default value to this attribute, in essence, what happens is when we construct a new pizza object, this attribute would initialize to false, or when we go to read it, it would initially be false. And so if we did that, we wouldn't have to initialize extra cheese, if it were already false. We would only have to change it if it were true. And so it's possible to have default attribute value. One way that we could prove this and play with this is, if I go to the REPL, I could make a new pizza, like a pizza in my REPL. And we can see a pizza dot extra cheese is bool, but if I were to test, well, what is a pizza dot toppings? We would see that that attribute, it looks like it doesn't even exist because we haven't initialized it yet. So we would get an attribute error. We'll learn other ways of making it possible to construct pizza objects, and at the point of construction, go ahead and initialize the size and the topping so we don't leave it to chance, but we have more control than assigning a default value like we're seeing here. All right? Any questions on classes, objects? Big picture idea. Classes define the idea of something, like the idea of a pizza in our restaurant, or what customers can order. But it's not until you construct objects that you can start using pizza objects or treating them as existing in memory and start customizing their attributes. The class defines the attributes that all instances have, as well as what we've seen here, capabilities. We'll continue to look at object-oriented programming and add some more detail here on Thursday. Great work today as we introduce this new topic.